Okay, so exam 1, part 1, let's go ahead and run through this. So for problem 1, we have these two functions, and we want to find this limit of the function u of x as x goes to 0, justify your reasoning, and state any theorems that are applied. So clearly we should be using the squeeze theorem. So um, let's see, how should we phrase this? So, well, squeeze theorem means we want to then take the limits of the two bounding functions. So cosine of x, and then if we take that limit, we're going to get cosine of 0, which is 1. Now, if we take the limit as x goes to 0 of the x squared plus 1 function, that's also going to be 1. And so then we say, by squeeze theorem, uh, by squeeze theorem, this squeeze theorem will tell us that the limit as x goes to 0 of the function u of x must be equal to the same number that the um, two other limits take on. Okay. For number 2, looks like we've got just a bunch of limits, and what's graphed for us is the function g of x. Okay, so I'm looking at the -1. I'm approaching from the left-hand side, so that's going to go to infinity, uh, positive infinity. So I'll just write infinity. This one is approaching from the right-hand side. We're going to get the value 4. For C, it's asking for the two-sided limit. Now, these two are not equal, so this two-sided limit does not exist. And then g of -1, let's take a look. So we have a filled-in circle here, which means if we plug in, we actually take on that value. So in this, for part D, this is equal to 4. Okay. Um, x 5 from the left-hand side, so that's going to there. That is the value 4. For the right-hand side, that's the value 2. Okay. And then the two-sided limit, again, these two don't give the same value, and so the two-sided limit does not exist. Okay, and then lastly, plugging in at 5. So, okay, here, notice that we don't actually have a filled-in circle anywhere. So the function g of x is actually undefined for the value 5. So what we would say is that this does not exist. Okay. Number 3, consider the graph above, list the x-coordinates where the function is discontinuous. Okay. So yeah, you can just quickly look and see it's discontinuous at -1, at 2, this is a point discontinuity, and at 5. So we just need to list the x-coordinates. I guess we can answer in a full sentence. Discontinuous at x equals, what was it again? -1, 2, and 5. Okay. -1, 2, and 5. Great. Number 4, given these two things, find these limits. So the idea for this problem is you're supposed to be applying the limit properties. So you can push this limit through the quotient, and that's going to be limit of the numerator divided by limit of the denominator, and then you push through everything. But we can just short circuit it. We don't need to show all of our work, all of our steps. In the end, we're going to have limit of a, which is given to us. So we have 9 divided by limit of a, which is 9, and then plus limit of b, which is 4. It's all given to us. So that's 9 divided by 13, and that does not simplify, so you can just leave it as is. For b, similar thing. So this is going to equal the square root. So first you would pass the limit through the square root function, and then you split it over the product, and then you push it into the squaring. So you're going to end up with 3 squared times limit of b, which is 4. And so you get that. 9 times 4 is 36. And so you get 6. Yeah. Okay. 5a and b. Looks like this is going to be algebraic. So, actually, well, a we can just plug in, can't we? Because there's no problems with that. So 2 plus 2 divided by 8, which is going to be 4 over 8, which is 1/2. Okay. And then this one, well, clearly if I plug in, I'm going to get 0 in the denominator, which is not good. So what we should do is we should factor the numerator. And if we factor it, how does this factor? I want to 6 and 5, right? So then minus 6 plus 5. Yeah. X minus 6, and you see that there's a cancellation, so this is the limit as x goes to 6 of x plus 5, which is going to equal 11. Okay. Okay, and part C. Hmm. Okay, so here, if I were to plug in, I would get division by 0 in both of these things. What we should do is try to combine the two fractions. So the common denominator is going to have me multiply this fraction by y and have me multiply the other fraction by 3. So I will have 3, do I want to show extra steps? Let's not do that. Let's just write it. So 3 from this numerator, y from this numerator, and then we would just combine the fractions. The common denominator is 3y, y minus 3. And then notice that this is just the negative of this, so this simplifies algebraically to be minus 1 over 3y, which is then going to be negative 1 over 9. So we have that as our answer. Yeah. Oh, and that's it for part 1. Okay.